Assalamualaikum and hi students. Okay, so as for the last video of this first chapter, we will cover the last LO, which is to find extrema of simple functions. Okay. Basically, in this last video of chapter 1, we will look at the one of the famous applications of calculus, which is in finding local extrema of the functions. Okay, so what is extrema? Extrema is referring to either maximum or minimum of functions. So first, let's see what is the definition of local maximum and local minimum. So definition 1.10, a function z f(x,y) is defined in a domain D and point A, B in domain D. Okay, so first, local minimum if is when FAB is less or equal to fxy for all points in a region R, where R is set of D. Okay, and second, this is the definition of local maximum if FAB greater or equal to fxy. Okay, local maximum correspond to mountain peaks. Okay, so if you refer to figure 1.8a, okay, so this is local maximum. And then a local minimum is here, corresponding to the valley bottoms of figure 1.8b. So this is how you see the local maximum and local minimum. If the function z is equal to fxy has a local maximum at AB, then fx AB equal to 0 and fy AB equal to 0. So this given by theorem 1.7 for first derivative test for local extrema. So let a function z equal to fxy is a local minimum or local maximum at point AB. So if fx AB and fy AB exists, then both fx and fy is equal to 0. Okay, this has been proved by theorem 1.7. But if fx and fy equal to 0, there is no guarantee that a local extrema has been located. Because if we see this example 1.9 here, we see both fx equal to 0, fy equal to 0. But this is not either local maximum or local minimum. The point 0, 0 and f0, 0 of this function is actually a saddle point. Okay, what does it mean by saddle point? Saddle point is when the critical point is neither local maximum nor local minimum. So that is what we call as saddle point. Next, the points AB such that fx AB equal to 0 and fy AB equal to 0 are called critical points. Okay, that point I mentioned before. Okay. The following theorem is used to determine if the critical points are local maximum, local minimum or a saddle point. Okay, that's why we cannot use the first derivative test. Instead of using the first derivative test, we use the second derivative test for local extrema. So for theorem 1.8, for a function z equal to fxy with fxx, fyy and fxy all exist on a region R and AB is a critical point. Okay, AB is a critical point in R. Define GAB. Okay, GAB means you need to find the determinant of this matrix. Okay, fxx, fxy, and then again we have fxy here, fyy. Okay, for point AB. So this is basically equal to fx multiplied by fyy, fxx multiplied by fyy minus with fxy multiplied by fxy. Okay, so this is minus. So that's why we have this one. Okay, so there is 4 conclusion can be made from your G and fxx. Okay, first, if GAB, if this value is greater than 0, so it is either local minimum or local maximum. Then refer to fxx value. If fxx value is greater than 0, so it is local minimum. But if it is less than 0, so it is a local maximum. Okay, and the third conclusion is if GAB is less than 0. So it is a saddle point. It's neither local minimum nor local maximum. Okay, and the last conclusion that can be made is if GAB is equal to 0. So there is no conclusion. That's it. To make it clear on how to find the local extrema, using the theorem 1.8 before, so we have two examples here. So let's start with the first example. Okay, for the first example, you need to find the critical points of fxy equal to 3x squared minus 2xy plus y squared minus 8y. Consequently, determine whether the critical points have a local maximum value, local minimum value, or a saddle point. So basically, we have 4 steps here. And then in finding local extrema, you need to use your knowledge in partial derivative. Okay, so let's start with the first steps. The first steps is to find all the partial derivative. Okay, so fx is equal to, find the fx here, we have 6x minus 2y. And then find fy. Fy is equal to minus 2x plus 2y minus 8. And then find fxx equal to 6. And your fyy is equal to 2. Okay, then fxy. From x, find fxy. Fxy is equal to minus 2. Okay, and then after that, you need to find what is the critical value. To find the critical value, fx must be equal to 0 and fy must be equal to 0. So fx is 6x minus 2y equal to 0. And then you have fy, which is equal to minus 2x plus 2y minus 8 equal to 0. Okay, from here you have y is equal to 6x over 2. So this is equal to 3x. Okay, so let this be your first equation. And then from here, you have 2y equal to 8 plus 2x. So your y is equal to 4 plus x. And this is second equation. So now you have the two equations here. Solve them simultaneously. So this is y equal to 3x. And you have another y equal to 4 plus x. Okay, from here you have 2x equal to 4. Moving your x to the left hand side, you have 2x equal to 4. Last, you have x equal to 2. Okay. Then substitute x equal to 2 into 102. Okay, so substitute into 1, let's say. This one, you have y equal to 3 multiplied by 2. So you have here 6. Now you have the value of x equal to 2 and your y equal to 6. So the conclusion is so you find your critical point. So the critical point is at x equal to 2, y equal to 6. So this is the first step. Second steps. Okay, for the second steps, you need to compute fxx at your critical point. So your critical point is 2, 6. So 2, 6. fyy at 2, 6. And then fxy at 2, 6. Okay, so fxx at 2, 6 is equal to, okay, so fxx is 6. Substitute 2, 6 is equal to 6. fyy 2, 6 is equal to 2. So substitute the value of x and y, you have 2. And the last one, for x, y, 2, 6 is equal to minus 2. Substitute x and y. This is minus 2. Okay, so that's it for second steps. Okay, next, moving to the third steps. For the third step, you need to find G, 2, 6. Okay, so the formula for G, 2, 6. This is equal to determinant of fxx. Okay, and then you have fxy here, negative 2. Another fxy here, and then you have fyy, 2. Okay, so this one, 6 multiplied by 2 minus 2 multiplied by minus 2. So you have 12 minus, this is 4, positive 4. And this is 8, where 8 is greater than 0. Okay, the last steps here, step 4 is for the conclusion. Okay, so for conclusion, okay, we refer to theorem 1.8, second derivative test. So for the second derivative test, you need to check your G and your fxx. So in our example, since G 2, 6 is greater than 0. Okay, so since it is greater than 0, so it is either local minimum or local maximum. And next, look at our fxx 2, 6. Our fxx 2, 6 is equal to 6, and 6 is greater than 0. Okay, so both GAB and fxxAB is greater than 0. So our point is a local minimum. Okay, so what the conclusion is, thus f26 is a local minimum. Okay, so this is the 4 steps of solving the local extrema. As for the second example, we will look at a problem with multiple critical points. Okay, so locate all the critical points of fxy, xy plus x cubed over 3 minus y squared over 2 minus 2y plus 4. Then determine whether the critical points have a local maximum value, local minimum value, or a saddle point. Okay, let's start with first step. Okay, first step is to find all the fx is basically equal to y plus 3x squared over 3. So this is equal to y plus x squared. Then find the fy. Fy is x minus 2y over 2 minus 2. Then from fx, we find what is fxx. Fxx is equal to 2x. And then fyy is equal to minus 1. Okay, this one, we have y. This is x. Okay. Next, we find fxy. So for fxy, we have 1. Okay. Then find the critical point. For critical point, set our fx equal to 0 and our fy equal to 0. So y plus x squared equal to 0. So y equal to x squared minus x squared, sorry. So this is our first equation. And then for fy, x minus y, okay, so this can be cancelled out, minus 2 is equal to 0. So x is equal to y plus 2. So this is second equation. Solve them simultaneously. So what we can do is to substitute 1 into 2. Okay, so 1 into 2, x is equal to y. Our y here is minus x squared plus 2. Okay, so we have x squared plus x minus 2 equal to 0. Okay. So solving for x squared plus x minus 2. So we know that we have two roots here because we have a quadratic function. So this is x plus 2, x minus 1 equal to 0. So the first x is equal to minus 2. The second x is 1. Then from here, substitute when you have x equal to negative 2. So your y is equal to, substitute here, so you have negative 2 square. Sorry, this is negative, okay, this is negative 2, you have negative here. So you have negative 4. And when x equal to 1, you have y equal to negative 1 square, which is equal to minus 1. So the two critical points you have here are, okay, the critical points are negative 2, 4, negative 2, negative 4, and 1, negative 1. So we are done with first steps. Moving to the second steps. For the second step, so what you need to do is to find the value for fxx for your critical point. So negative 2, negative 4. And then what is xy for negative 2, negative 4. Then you need to find what is fyy for negative 2, negative 4. And then since you have two critical points, so you need to find fxx for 1, negative 1 as well. fxy for 1, negative 1. And fyy for 1, negative 1. So fxx is 2x. Substitute the value of negative 2, negative 4. So you have negative 4 here. fxy is equal to 1. So it is always 1. fyy is equal to negative 1. So it is always negative 1 because we don't have any variable here. So fxx 1, negative 1. Substitute 1 into x. So we have 2. This is equal to 2. We have here 1 and negative 1. So done with second steps. The third steps, okay, for the third steps, you need to find the g. Okay, find the g for first point, negative 2, negative 4. Okay, so this is equal to, we substitute. So here we have negative 4. Okay, we have 1 here, over here, and then 1 over here. We have fyy here. For g, negative 2, negative 4. So this is equal to minus 4 multiplied by minus 1 minus 1 multiplied by 1. So this is 4 minus 1 and equal to 3. 3 is greater than 0 for the first critical point. Then for the second critical point, which is 1, negative 1, we have 2 over here, and then 1, 1, then we have negative 1 here. For this one, we have 2 multiplied by negative 1 minus 1 multiplied by 1. So negative 2 minus 1 is negative 3, and negative 3 is less than 0. Okay, so now you have your g and fxx. So we can move to the conclusion. So since we have two critical points, so we have two conclusions. The first conclusion is refer to the first point. Okay, so since g minus 2 minus 4 is greater than 0. Okay, so if g greater than 0, okay, look at the fxx. So and then fxx for negative 2, negative 4 is equal to negative 4. Negative 4 is less than 0. So less than 0. Thus, f negative 2, negative 4 is a local maximum. Because you have fxx less than 0. And then second conclusion for the second critical point, since the g negative 2, negative 4 is less than 0. Okay, so look at the third conclusion. G is less than 0. So automatically the FAB is a saddle point. Okay, so this is how we solve for the local maxima. So that's all for this chapter 1. Okay, we have done with chapter 1. So in the next video, we will start the new chapter, which is chapter 2 on multiple integrals. Thank you.